But you can take other X contributions, his conjectures, and how they impact the meta complexity, and sort of interpret this.
Thank you so much. Thank you so much for having me. It's quite a pleasure to give a presentation here because I'm very influenced by Eric's work. So I'd like to celebrate Eric's fundamental contributions to meta complexity. So today, what I'm going to talk about is about Eric's two conjectures. So he wrote a paper in CRE, which is a computability conference in Europe. And this is a paper from Eric's CRE paper. And he has this conjecture. So the title of the paper is Curious and Curious, the link between incompressibility and compressibility. And what he conjectured in his paper is that he conjectured that compressive classes NEXP and BPP can be characterized in terms of a reduction to the set of Kolmogorov random string, which is denoted by R here. This paper was quite influential to me because I started working on compressive theory by trying to prove these conjectures. So that was my first paper. And today, I will not talk about this first paper, but I would like to explain recent progress on these conjectures and its impact that these conjectures have on meta complexity. So what's this paper about? Well, he proposed to understand the relations between two notions of randomness in compressive theory and computability. In compressive theory, we have a familiar notion of randomness, namely BPP. Remember that this is a class of problem that can be solved efficiently by using randomness, namely random coin flips sequence. On the other hand, in computability theory, we have a quite different notion of randomness, namely Kolmogorov randomness. And then what he tried to do is to try to understand BPP through the lens of computability or Kolmogorov randomness string. So that's what he proposed in his paper. So in order to state his conjecture, let me define what is Kolmogorov complexity. So remember that Kolmogorov complexity is in this talk, I'm going to use the notation K sub u of x is over a finite string x is the shortest program size to print the string x. But for example, let's consider all zero string of length n. You can describe this string by a short program saying that print 0 n times. So the Kolmogorov complexity of this string is at most log n to represent this binary encoding of n plus additive constant. On the other hand, there is a fundamental property of Kolmogorov randomness, which says that if you choose uniformly at random string, then with high probability, the Kolmogorov complexity is maximum. Namely, the Kolmogorov complexity of a uniformly chosen string R is close to the length of R. Now, so this is the idea of Kolmogorov complexity. But in order to formally define the notion of Kolmogorov complexity, we need to fix an interpreter U. Namely, there are several programming languages, and depending on what programming languages you use, you have a slightly different variant of Kolmogorov complexity. So in general, for any Turing machine U, we can define the Kolmogorov complexity of a finite string x with respect to the Turing machine U. And we can define as follows. It's the minimum of a discretion length D, such that U outputs x given input D. So think of D as a program that prints x. And it's known that if you take a universal Turing machine, you can get a Kolmogorov complexity that is shortest, smallest up to additive constant. More generally, we can call such a Turing machine universal. So we say that Turing machine U is universal if it's the smallest among any other Kolmogorov complexity measure. Namely, for any Turing machine M and for any string X, the Kolmogorov complexity defined with respect to U is at most the Kolmogorov complexity of X defined with respect to the other Turing machine plus additive constant. In that case, we say that Turing machine is universal, and it is known that there is a universal Turing machine that simulates any other Turing machine. So this is a notion called Kolmogorov complexity. And once you define the notion of Kolmogorov complexity, we can define the notion of randomness in computability theory, namely Kolmogorov randomness. So we say that the string is Kolmogorov random if it can't be compressed into a shorter program. Namely, if the Kolmogorov complexity of X is at least the length of the string itself, then we say that the string is Kolmogorov random. And I'm going to use a notation R sub KU, which is a set of strings, set of Kolmogorov random strings. For example, if you look at the all zero string of length n, as we saw, this can be compressed into order log n bits of a program. So you can compress it, so it's not Kolmogorov random. On the other hand, if you pick a uniform random string with high probability, it's going to be a Kolmogorov random, which can be shown by a simple counting argument. Now, so we have two different notions of randomness in complexity theory and computability theory, but there is no relationship among them in the sense that it's easy to see that the Kolmogorov random string is not computable. So by a simple argument, you can show that Kolmogorov complexity is not computable, as well as you can't compute this set in finite steps. So there is no obvious relationship among them. And what he suggested is to try to bridge the gap, these two different notions, by considering efficient reduction to the set of random string. So let me explain how we can bridge the gap between non-computable sets and something that is computable. So the point is that we consider reductions to Kolmogorov random string. So let's consider the following situation. You have a polynomial time Turing machine, which can make non-adaptive queries to the set of oracle, namely the set of random strings. And we'd like to solve a problem L. Now, you are allowed to make non-adaptive queries asking whether Q is in the set of random string, and given answer from the oracle, we would like to decide the language L. So let's denote this class by P parallel reduction to the set of random string. So this subscript parallel means that we are restricting the Turing machine to non-adaptive reductions. Now, once we define, so what we are asking here is that what can be solved efficiently by non-adaptive asking whether the query is in random string or not. Now, Berman and Fortner-Koskinen-Roth showed that BPP is contained in this class. Namely, if you have an efficient algorithm that solves L by using coin flips, you can somehow replace these coin flips by using this oracle, Kolmogorov random string oracle. Now, the question is, what's the upper bound? So this is, in some sense, one side connection between BPP and Kolmogorov random string. But the question is, what is upper bound for this class? Obviously, the set of Kolmogorov random string is not computable. So there is an uncomputable set in this class. So there is no obvious upper bound on this class. But what Eric suggested is to take the intersection over all universal Turing machine. Then you get somehow you get a p-space upper bound. So here, what we are asking for is that this class corresponds to this. If a problem is in this class, it means that you can reduce the problem to the set of random string, no matter what kind of universal Turing machine you use. So in some sense, this asks what can be reduced to the set of random strings. irrespective of what kind of universal Turing machine you use. Then somehow you get p-space upper bound. So given this connection, yeah.
So if I have a polynomial time deterministic machine, like how could I ever get an interesting response out of a query to the Kolmogorov random oracle, right?
Yeah.
Like if I'm going to be asking a string, isn't the complexity of that thing going to be low necessarily? Like why doesn't it always go up to 0?
Yeah, that's a good question. I will go back to that.
Maybe the string you're given as input
Very short.
has high Kolmogorov complexity.
Yeah, so that's very good intuition. Well, I will explain it later. I will explain it in the next slide. That's very good point. So yeah, now we have a lower bound and upper bound. So a natural question is which is tight, and what Eric conjecture is that the lower bound should be tight. So Eric conjecture that BPP should be characterized through the lens of Kolmogorov complexity in this sense. Namely, BPP is a set of the class of languages that can be non-adaptively reducible to the set of Kolmogorov random string. That's Eric's conjecture. And before talking about the intuition behind this conjecture, so actually the intuition behind this conjecture is what Robert asked, and I will explain later. But why should we care about this conjecture? Well, there are a couple of motivations, but perhaps one of the most important motivation is that this is closely related to a minimum circuit size problem with halting oracle. So this is a very influential paper by Eric and others, which show that if you have a circuit complexity with halting oracle, then it's polynomially related to Kolmogorov complexity. So in some sense, this shows that MCSP is not NP-hard under non-adaptive reduction in the sense of computability theory. Another interesting motivation is that Eric speculated that this might be an approach towards P equals BPP conjecture. And in fact, you can improve this p-space upper bound if you restrict the power of the reduction somehow to what is called disjunctive true-stable reduction. In that case, you get an upper bound of P as well. So so by studying this conjecture, he speculated that this might be an approach towards P equals BPP conjecture. Now let me get back to Robert's question. So why this conjecture seems to be true? So let's say you have a polynomial time machine, but let's restrict ourselves to inputs, unary input, 0 to the n. Now, if you consider any query that this Turing machine can make, the Kolmogorov complexity of any query is actually order log n. The reason is that given input n, you can generate this set of queries in polynomial time. So you can specify each query by having n and the index of a query. So that's why we get this upper bound. Now, this means that for most of the time, you get no answer from the oracle. Namely, if the query, the length of a query is larger than order log n, then the answer from the oracle must be no. So that's the intuition why Eric's conjecture seems to be true, because on input 0 to the n, any polynomial time non-adaptive reduction cannot make use of any query of length larger than order log n. Now, let me quickly recap complexity classes. So you have a P, BPP, NP, co-NP, and a PH. Remember that PH stands for polynomial hierarchy, and you have P space. Now, what we would like to understand is this complexity class. And this complexity class looks very weird, and at least it is sandwiched between BPP and P space, and we would like to understand what's this complexity class. Now, because Eric's intuition comes from when you restrict yourself to input of a unary input. So let's focus on input 0 to the n. And by a standard padding argument in complexity theory, this is essentially equivalent to considering exponential time analog of these complexity classes. So let's consider exponential time analog of these complexity classes. So if you have a P here, you get exponential time, EXP here. And if you have a PH here, you have EXPH. This is the exponential time hierarchy. Now, what we can show is that actually, if you look at exponential time analog, the complexity class looks quite nicer compared to the polynomial time analog. And we can actually show that this complexity exponential time analog of this complexity class is sandwiched between EXPH and EXP space. So it's much larger than BP-EXP, which was conjectured by Eric. So in ITC's paper, we showed that EXPH can be reducible to the set of Kolmogorov random string by using non-adaptive exponential time reduction. So what this means is that by a simple padding argument, you can refute Eric's conjecture. Namely, unless exponential time hierarchy collapses to BP-EXP, we can show that Allender's conjecture is false. Namely, BPP is not equal to this complexity class. So that's one result about Eric's conjecture. And there are other several conjectures which also tries to understand complexity classes through the lens of Kolmogorov random strings. So if you consider adaptive reduction, you get a lower bound of P space and upper bound of EXP space. And similarly, if you consider non-deterministic polynomial time reduction, you get a lower bound of NEXP and EXP space. And it was conjectured that the lower bound should be tight. Namely, in the hypothesis put forward by Eric and others, P space should be characterized the set of the class of problem reducible to the set of random string. And Eric also conjectured that NEXP should be characterized by using the reduction to the set of random string. Actually, unfortunately, these two conjectures are false unless EXP to the NP collapses. So we were able to, in a stock paper, we were able to show that EXP to the LP, which is much larger than P space, can be reduced to the set of random strings. So in particular, unless EXP to the NP is contained in NEXP, P space can't be characterized by this complex class, and the NEXP can't be also characterized by this complex class. Yeah.
Repeat the question.
So the question is, what's the intuition behind why this conjecture is false?
Or sorry, the original intuition.
Yeah. Yeah, that's a good question. So the intuition is that basically you are restricted to just asking order log with length queries, but somehow you can get information such as satisfy the lexicographically first certificate for SAT by making a query of this length. So yeah, it's a bit difficult to explain, but I will explain the proof idea later. So yeah, that's yeah, could be. Yeah, I think that's much. Yeah, if you have a larger gap, the condition might. Yeah, that's a good point. So, yeah, paper by Sachs and Sansalam, they showed that if you restrict honest reduction, you get some kind of upper one, some improved upper one. So yeah, I think if you restrict to the class of reductions, you might still get this kind of characterization. Okay, so yeah, we have this. Previously, we had P space, but we now have EXP to NP, and we still don't understand what's the right answer for this. So let me explain the proof idea, but for different results from the same paper. So I'm going to present a proof for NP-hardness of Kolmogorov complexity and quasi-polynomial time non-adaptive reductions. So here, I'm going to consider a slightly stronger oracle here. So we assume that the oracle returns Kolmogorov complexity of query Q instead of asking the set of random string. So the reason why I'm going to present this is that in some sense, this can be seen as NP-hardness of MCSP with porting oracle. So that might be interesting to you. And also the proof is inspired by ITC paper. So the proof contains some idea why LX conjecture is false. And there are two important ingredients for the proof. So one is symmetry of information. Symmetry of information states that Kolmogorov compressed of y given x plus the compressed of x is approximately equal to the compressed of x and y. And another ingredient in the proof is what is called K-wise direct product generator. So let me explain what is this generator. So K-wise direct product generator, which I'm going to denote by dp sub k, is the following very simple function. So this function takes a string x and g1 up to gk, and it outputs g1 up to gk, and it also outputs g1th bit of the error-corrected version of the function of the x. So here, enc is some list decodable error-correcting code, and it outputs a string of length 2 to the lambda. So you can think of gi as an index to the string, to the bit of a string. And here you output the gi'th bit of error-correcting code of x. And it is known that we can choose error-correcting code to output polynomial lengths. So we can assume that lambda is order log lambda or order log n. So if you know what is a pseudo-random generator construction, this can be think of a pseudo-random generator construction based on a hard truth table of x. And this pseudo-random generator takes a seed of lambda k bits and extend it to by k bits. So it outputs the lambda k plus k bits. And the reason why we call this pseudo-random generator construction is that we have a reconstruction procedure for this direct product generator. So what it says is that, let's say you have a oracle D and you have a string x, and let's say D can distinguish the pseudo-random sequence dp sub k from the uniform distribution. In that case, you can show that there is a compressed representation of x of order lambda k bits. So here I haven't explained what is time-bounded Kolmogorov complexity, but this says that the time-bounded Kolmogorov complexity of x is at most order lambda k. And what it means is that there is a polynomial time program with D oracle of length order lambda k bits that prints x. In other words, it might be easier to understand this in the contour positive way. So if you take the contour positive, it means that if you don't have any compressed representation of x, then you cannot distinguish the pseudo-random sequence from the uniform distribution. So that's why we call this pseudo-random generator construction. And the proof of this reconstruction is just a simple hybrid argument, which you can prove by yourself if you are familiar with pseudo-randomness. But in this talk, let's assume that this is true. And let's see how we can prove NP-hardness of Kolmogorov complexity. let's say you have a language L that you want to solve, and you have a verifier for the language. And let's say you have an input X. And let's say you have a, so the idea of the proof is that we would like to find the first certificate, reciprocally first certificate on input X, on yes instance for X. So let's say Y sub X is the first certificate, and the goal is to find the certificate. Now, how can we do that? Well, the idea is to try to distinguish the pseudonym generator construction that is instantiated with Y sub X from the uniform distribution. So the idea behind this is that if you know the reciprocally first certificate, you can distinguish this pseudonym sequence from the uniform distribution. So that's a kind of high-level intuition. Now, since we have a Kolmogorov compressed oracle, it's natural to try to break this pseudonym generator by measuring Kolmogorov complexity of the string. So let's measure Kolmogorov complexity of X and dp sub k, which is instantiated with Y sub X. Now we can bound this complexity by Kolmogorov complexity of X plus the length of the seed Z and the log k bits in order to encode k here. So the reason why this is true is that let's say you have a program that prints X. Now you have X, and if you have X, you can find by using exhaustive search, you can find Y sub X. Now, if you are given Z as well, you can compute the direct product generator. So in this way, we get this upper bound. Now, remember that the seed length is k times lambda, where lambda is order log n. So we get this upper bound. On the other hand, we also have a lower bound. Let's say instead of direct product generator, let's consider a uniform distribution W. In this case, by using a symmetry of information, we can lower bound this by Kolmogorov compressed of X plus the Kolmogorov compressed of W given X. And if we choose W from the uniform distribution, then by a simple counting argument, we can show that this Kolmogorov compressor is close to the length of W. And the length of W is k lambda times k. So we get this slightly larger threshold. So this means that if we measure Kolmogorov compressor of these strings, we can distinguish pseudo-random sequence, or if you choose k to be sufficiently large, namely k can be chosen to be order log n. Now we can define oracle as follows. Let's say you have a threshold S here, and we can define an oracle dx as follows. Its output 1 if and only Kolmogorov compressor of X and W is small. And by this argument, we know that this output 1 on every input in the range of the direct product generator. And from the second argument, we can show that if you get uniform input, then you get you output 1 with small probability. Now, by using the reconstruction procedure, we get a compressed representation of the reciprocally first certificate. Namely, Y sub X, Kolmogorov compressor of Y sub X is at most order k times lambda, and k is order log n, and lambda is order log n. So we get an upper bound of order log n squared. So now we get an efficient algorithm for solving NP. The algorithm is quite simple. So given X, we just try to find a reciprocally first certificate by trying all possible compressed representation of the Y sub X. Namely, we try all possible polynomial time program of size log n squared and check if it is a certificate for X in the yes instance. So that's the proof. So in order to get the result in ITCS paper, this is in some sense special case in which you consider X being unary. And in that case, the threshold S becomes order log n. So in some sense, you get you can replace Kolmogorov compressive oracle with the oracle of the set of random strings. Another special case is a case of X is chosen randomly from the uniform distribution. And in this case, we also get a heuristic algorithm for solving the NP by using the set of random string as an oracle. The reason is that you get, in this case, the threshold can be chosen close to the maximum. So that's an idea. So so naturally you get some kind of average case algorithm, and this paper led me to writing another paper, which connects two areas of compressed theory. So one area is average case compressed of pH, which is pioneered by the work of Levin. For example, one of the fundamental questions in compressed theory is whether pH is hard on average. Another question in compressed theory is what is meta complexity of computing time-bounded Kolmogorov complexity. So this is pioneered by Terry Cole, the paper, and the question, a specific question you might ask is what is the complexity of approximating pH oracle time-bounded Kolmogorov complexity. And by using the idea developed in the previous work, in a Fox paper, we were able to establish the equivalence between these two questions. So we get interdisciplinary link between average case complexity and worst case complexity. Namely, the following statements are equivalent. One is that distribution of pH is not in average P, which means that pH is hard on average. And this is equivalent to the worst case hardness of approximating pH oracle time-bounded Kolmogorov complexity, which is denoted by gap mutated pH. So why this is interesting? Well, from the perspective of meta complexity, this result classifies the complexity of gap mutated pH as a distributional pH complete problem in the sense of this equivalence. And from the perspective of average case complexity, this provides a new proof technique of analyzing average case complexity by using meta complexity. So, and as a specific application, we get a hardness amplification theorem for pH. So in the next slide, let me explain what is gap mutated to pH. Mean KT, which is defined by Cole, the paper, is a problem of computing the time-bounded Kolmogorov complexity. And T time-bounded Kolmogorov complexity of X is the length of the shortest program that prints X in T steps. And mean KT is a problem of computing T time-bounded Kolmogorov complexity. And naturally, we can consider A oracle variant of the problem, which is called mean KT to J. So we can generalize T time-bounded Kolmogorov complexity to A oracle time-bounded Kolmogorov complexity. So instead of asking the shortest program that prints X, we are considering A oracle shortest program that prints X. And this is denoted by K supercapital T and X, A. And mean KT to A is a problem of computing A oracle time-bounded Kolmogorov complexity. You might imagine that A should be reducible to mean KT to the A, but this, unfortunately, this is not known, and it would have a significant consequence if you can prove this. And it's easy to see that this is a problem in NP to the A. Now, let me state this result slightly more formally. So this statement means that for every oracle A in PH, gap indicated is in P. Namely, you can approximate A oracle time-bounded Kolmogorov complexity in polynomial time. And here, gap means that we are allowing order log n additive error gap in the approximation. And as a corollary of this equivalence, we get the new techniques of analyzing average case complexity by using meta complexity. So what this gives us is that let's say you have average case algorithm for PH that succeeds on 1% of a fraction of inputs. Then can we get average case algorithm that succeeds 90% of the algorithm? This is called our average case hardness amplification. And in order to prove this, so this can be obtained by as a corollary of this equivalence. And this equivalence can be proved as follows. First, you use assuming that pH is easy on average, and this algorithm succeeds on just 1% of inputs. You use worst case average reduction to get the worst case approximating algorithm for gap indicated pH, which I will not explain today. But then if you have an efficient algorithm that approximating Kolmogorov complexity, then you get average case algorithm that solves pH. So this is based on the ideas developed in refuting Eric's conjecture, and the proof is pretty much the same with the previous proof. So let me explain how we can move from worst case meta complexity to average case complexity. So the proof is quite similar to the previous one. So let's say gap indicated to the NP is in P, and let's say we'd like to prove that this NP is easy on average. We haven't explained what is this NP is, but what I'm claiming is that previously we considered the worst case input, but now we are taking a uniform random input, and we would like to show that you can solve NP on average for random input. So the proof is quite similar to the previous one, and the difference is emphasized in red. Again, the goal is the same, so we'd like to distinguish the direct block generator. But now we don't have time unbounded Kolmogorov compressed oracle. Instead, what we have is a SAT oracle time bounded Kolmogorov complexity. I'm going to show you how to distinguish a direct block generator by using NP oracle time bounded Kolmogorov complexity. So the point is that previously we didn't have any time bound. Now we have a polynomial time bound. And in order to find a first certificate, it takes exponential time. But if you have a SAT oracle given X, you can find the first certificate in polynomial time. So we can use the same calculation as before, and we get the upper bound of n plus k lambda. On the other hand, if you consider in order to lower bound Kolmogorov complexity of X and W, we use a simple counting argument because here, and we get a lower bound of n plus k lambda plus k. And just as in the previous proof, we can show that this time-bounded Kolmogorov complexity can distinguish direct block generator from the uniform distribution. Now, we just as in the previous case, we can define an oracle d sub x to output 1 if and only if time-bounded Kolmogorov complexity of X and W is somehow small. And then we can show that we get a compressed representation of y sub x. And if you apply the previous reconstruction, you get something like order log n squared. But you can improve this by using compressed theoretic Solomon generator. And this is actually the most technical part in the paper, but let's forget about it. Now you get the upper bound of k plus order log n, which is order log n. So we get to the following simple algorithm. Given a random input x, we just enumerate all possible polynomial time program of size order log n, and we check whether the output of the universal Turing machine is a certificate for the x being in L. So in this way, since it takes 2 to the order log n time to do exhaustive search, you get a heuristic polynomial time algorithm for NP. And so, yeah.
So where is the randomness of x used to?
Yeah, that's a good point. Where does the randomness is used is basically here. So in this part, we get the upper bound of n, and on the other hand, we need upper bound, lower bound of n here. And the way we argue here is that we use time analytic Kolmogorov complexity. So that's why we need to this only holds for random input x. That's a bit subtle, but yeah, that's it.
It's possible to say a few words on what's special about the generator here, like why couldn't we use?
Yeah. So the question is why we are using direct product generator. So that's a very good point. So direct product generator achieves the minimum advice complexity here. So this is called advice complexity, and the direct product generator is in some sense optimal in the sense that it's just k, which is the extension of seed. In general, there is a lower bound of k. So in this context, it's better to use direct product generator. Yeah.
Is there any
Well, yeah, that's a bit difficult. Yeah, if you can define oracle that this is to sequence, then yeah, you can argue in a way, but yeah, I'm not sure as a condition. Now, this idea led me to get new worst case to average case connection, which is a substituted paper in stock 2021 and 21. And in this paper, we get a new worst case to average case connection. For example, assuming that pH requires the time complexity 2 to the order n by log n, then pH is hard on average. And similarly, here n is the input length of the problem. And similarly, we can show that NP, if NP requires the time complexity of 2 to the order n by log n, then NP is hard on average in a certain sense. So here, average sub PP is a notion that interpolates worst case P and average P. And this is, informally speaking, this is a class of a problem that can be solved by average case polynomial time, whose running time can be estimated efficiently. In some sense, this excludes a strong variant of a heuristic. So let me explain how we can prove this kind of result. So the proof idea is quite similar to the previous one. So let's say we'd like to prove that, assuming that pH is easy, we'd like to solve pH in the worst case. And just like as before, we use the idea of meta complexity as a catalyst. And first, we use worst case to average case reduction to get some worst case algorithm to approximate pH oracle time analytic complexity. And then again, by using the idea that I showed in the previous proof, we can construct what is called a universal heuristic scheme. which is some worst case, in some sense, worst case algorithm for pH. And then we can get a worst case algorithm that runs in 2 to the order n/pi log n. So I haven't time to explain the detail, but if you are interested, there's my survey in ETS bulletin. So please refer to that paper. So going back to Eric's conjecture, unfortunately, we haven't been able to characterize BPP from the perspective of the reduction to Kolmogorov complexity. But if you consider non-interactive statistical zero knowledge, NISDK, we were able to give a characterization. So this is a joint work with Eric and Harsha. And we were able to show that non-interactive statistical zero knowledge can be characterized as a class of decidable language that can be reduced to approximation of Kolmogorov random string in a certain sense. And we can also characterize non-interactive statistical zero knowledge with log space verifier by using a reduction to Kolmogorov random strings where the reduction is randomized NC0. So it's quite efficient reduction. So we still, we haven't been able to find any application of this characterization, but that's a nice open question. So in conclusion, I'm very influenced by Eric's work, and I would like to celebrate Eric's fundamental contribution to metacomplexity. So thank you so much, Eric.
Question?
Yeah, so this is a set of random string, but you have this is defined in terms of approximation in the sense that yes instances is a set of random string. Yeah, let's say it's at most the length of yes instance string with high complexity, and no instance is a set of random string, but the string with small thermal complexity, and we get some additive error. So this is a promise problem, and if we have a efficient reduction to this problem, that characterizes.
So the fact that we moved it, if I'm ignoring the gap for a second, the fact that we moved it to x/2, should it make me think of the problem as easier, which explains the result, or just as hard and we were able to prove it for this problem?
I think it's there's a if you do a padding, there's a randomized padding reduction which enables you to change this threshold. So it's not so important what threshold you use.
Okay, so it's just the gap.
Yeah, the gap is very important.
Small gap.
Yeah, yeah.
So if you think of it as basically close to arcade gap, right? In terms of how hard this problem is, not how it gives.
Yeah. So previously we considered we take intersection over any universal Turing machine, but now we are allowing errors. So this you don't have to take intersection over universal Turing machine anymore, and this makes more clean.
Thank you.
Okay, yeah. Has anyone studied, like, I guess, classes of like problems reducible to, like, instead of deciding k complexity, like producing
random case string, like what problems can you solve if you can have an oracle that like gives you a string with high capability, but you don't control which one to get or not.
I see. That's a great question, but I don't think there's any.
Last question.
So one direction you showed works for NP, but the equivalence you stated for PH. So is it easy to see why you need to go to the hierarchy for the full equivalence?
Yeah, that's a good question. So in some sense, we are losing one quantifier in this reduction because gap communicated to NP is a problem in sigma to B, so it's a second level. But generally, the conclusion you get is just the first level. So that's why we get, we don't have good characterization for averages compressed wave. And so, this characterization we need to go up pH because if you go through this equivalence, you lose one level of hierarchy. That's no question.
Let's take other questions to the coffee break. Let's thank Shuichi again. So let's have a 10-minute coffee break and we'll resume at 20.